In a world where X wasn't even a letter yet, where solving equations was almost magic, among the pyramids, Alexandria teemed with ancient knowledge. There lived a man who dared to translate unknowns into answers, Diophantus of Alexandria. These symbols, their counterparts, and their mysteries have spanned centuries, but today we know almost nothing for certain. In this video, you will hear the story of a mathematician who lived among shadows and theorems, and understand why he is called the father of algebra. Shall we begin this journey? Stay with me until the end. It will be worth every second. The greatest mathematicians of all time. Episode 14. Diophantus of Alexandria. Diophantus, often referred to as the father of algebra, is best known for his Arithmetica, a work on the solution of algebraic equations and number theory. However, essentially nothing is known about his life, and there has been much debate about his actual dates. There are some limits that can be placed on the dates of Diophantus's life. On the one hand, Diophantus cites the definition of a polygonal number from Hypsicles' work, so he must have written this after 150 BC. On the other hand, Theon of Alexandria, Hypatia's father, cites one of Diophantus's definitions, so this means Diophantus wrote no later than 350 AD. However, this leaves a gap of 500 years, so we cannot narrow Diophantus's dates too much with this information. There is other information that was accepted for many years as providing fairly precise dates. Thomas Heath, in Diophantus of Alexandria, a study in the history of Greek algebra, quotes a letter from Michael Psellus, who lived in the last half of the 11th century. Psellus wrote, "Diophantus treated Egyptian arithmetic more precisely, but the highly learned Anatolius gathered together the most essential parts of the doctrine, as stated by Diophantus, in a different manner and in the most succinct form, dedicating his work to Diophantus." Psellus also describes in this letter the fact that Diophantus gave different names to the powers of the unknown than those given by the Egyptians. This letter was first published by Paul Tannery in Diophantini Alexandrini Opera Omnia cum Graecius Commentaries, and in that work he comments that he believes Psellus is quoting a commentary on Diophantus that is now lost and was probably written by Hypatia. However, the above citation has been used to date Diophantus using the theory that Anatolius, the bishop of Laodicea, was a writer and teacher of mathematics and lived in the 3rd century. From this it was deduced that Diophantus wrote about 250 AD, and the dates we have given for him are based on this argument. W.R. Knorr, in Arithmeticae Stoiciosis, on Diophantus, the hero of Alexandria, criticizes this interpretation. But we immediately suspect something is amiss. It seems peculiar that someone would compile a summary of another man's work and then dedicate it to him, while the qualification in a different manner, itself empty, should be redundant given the terms more essential and more succinct. Knorr gives a different translation of the same passage, showing how difficult the study of Greek mathematics is for anyone other than a specialist in classical Greek, which has a remarkably different meaning. Diophantus treated Egyptian arithmetic more precisely, but the very learned Anatolius, having collected the most essential parts of that man's doctrine, addressed it very succinctly for a different Diophantus. Knorr's conclusion regarding Diophantus's dates is,
we must consider the possibility that Diophantus lived before the 3rd century, possibly even before Hero, in the 1st century. Most of the details we have about Diophantus's life, and these may be entirely fictitious, come from the Greek anthology compiled by Metrodorus around 500 AD. This collection of riddles contains one about Diophantus that reads, "His life was long, a 1/6 of which was his beautiful childhood. Another 1/12 of his life had passed when his face was covered with hair, and the 7th part of his existence was spent in a barren marriage. Another 5 years passed, and he rejoiced at the birth of his beloved firstborn, whose beautiful life lasted only half that of his father, who, to everyone's great sorrow, went down to the grave 4 years after his son's burial."
He then married at 26 and had a son who died at 42, 4 years before Diophantus himself died at 84. Based on this information, we gave him a life expectancy of 84. Arithmetica is a collection of 130 problems that provide numerical solutions to determinate equations, those with a unique solution, and indeterminate equations. The method for solving the latter is now known as Diophantine analysis. Only 6 of the original 13 books are believed to have survived, and it was also thought that the others must have been lost soon after they were written. There are many Arabic translations, for example by Abulwatha, but only a few materials from these 6 books have survived. Heath writes in 2020, "The missing books were evidently lost at a very early date. Paul Tatery suggests that Hypatia's commentary extended only to the first 6 books and that she left untouched the remaining 7, which, partly as a consequence, were first forgotten and then lost." However, an Arabic manuscript in the Ustan-e-Quds Library, the Library of the Holy Sanctuary in Meshed, Iran, has a title claiming it is a translation by Kusta ibn Luka, who died in 912, of books 4 through 7 of Diophantus of Alexandria's Arithmetica. F. Servick made this remarkable discovery in 1968. R. Rashed, in Les Travaux perdus de Diophantus, compares the 4 books in this Arabic translation with the 6 known Greek books and claims that this text is a translation of Diophantus's lost books. Rosenfeld, reviewing these 2 articles, however, is not completely convinced. The reviewer, familiar with the Arabic text of this manuscript, does not doubt that this manuscript is a translation of the Greek text written in Alexandria. However, the great difference between Diophantus's Greek books on arithmetic, which combine questions of algebra with profound questions of number theory, and these books, which contain only algebraic material, makes it very likely that this text was written not by Diophantus but by one of his commentators, perhaps Hypatia.
It's time to analyze this remarkable work on algebra in Greek mathematics. The work considers the solution to many problems related to linear and quadratic equations, but considers only positive rational solutions to these problems. Equations that would lead to negative solutions or irrational square roots Diophantus considered useless. To give a specific example, he calls the equation 4 equals 4 times x plus 20 absurd because it would lead to a nonsensical answer. In other words, how could a problem lead to the solution minus 4 books? There is no evidence to suggest that Diophantus realized that a quadratic equation could have 2 solutions. However, the fact that he was always satisfied with a rational solution without requiring it to be an integer is more sophisticated than we might imagine today. Diophantus studied 3 types of quadratic equations.
The reason Diophantus had 3 cases, while today we have only 1, is that he had no concept of zero and avoided negative coefficients by assuming that the given numbers a, b, and c were all positive in each of the 3 cases above. However, there are many other types of problems considered by Diophantus. He solved problems such as pairs of simultaneous quadratic equations. Diophantus would solve this problem by creating a single quadratic equation in x. He began by setting y times x equals y minus z. Then, adding the equation y plus z equals 10 to the equation y minus z equals y times x, we obtain that y equals 5 plus x. Subtracting one equation from the other, we obtain that z equals 5 minus x. Now, using the product of y and z, we have that 9 equals y multiplied by z, that is, equal to 5 plus x times 5 minus x, which is equal to 25 minus x squared. Therefore, x squared equals 16, and x equals 4. This leads us to y equals 9 and z equals 1.
In Book 3, Diophantus solves problems of finding values that simultaneously make 2 linear expressions perfect squares. For example, he shows how to find the value of x that makes 10 times x plus 9 and 5 times x plus 4 both perfect squares. He finds x equals 28. Other problems seek a value of x such that certain types of polynomials in x up to the 6th degree are perfect squares. For example, he solves the problem of finding x so that x cubed minus 3 times x squared plus 3 times x plus 1 is a perfect square in Book 6. Also, in Book 6, he solves problems such as finding x so that simultaneously 4 times x plus 2 is a perfect cube and 2 times x plus 1 is a perfect square, for which he easily finds the solution x equals 2/3. Another type of problem that Diophantus studies, this time in Book 4, is finding powers between given limits. For example, to find a square between 5/4 and 2, he multiplies both limits by 64, identifies the 100th square between 80 and 128, thus obtaining the 25/16 solution to the original problem. In Book 5, he solves problems such as writing 13 as the sum of 2 squares, each greater than 6, and provides the solutions 66,049 over 10,201 and 66,564 over 10,201. He also writes 10 as the sum of 3 squares, each greater than 3, finding the 3 squares 1,745,041 over 505,521, 1,651,225 over 505,521, and 1,658,944 over 505,521. Heath analyzes number theory results that Diophantus clearly knew about, but it is unclear whether he possessed a formal proof. Of course, these results could have been proven in other books written by Diophantus, or he could have considered them obviously true due to their experimental evidence. Among these results are: no number of the form 4 times n plus 3 or 4 times n minus 1 can be the sum of 2 squares. A number of the form 24 times n plus 7 cannot be the sum of 3 squares.
Diophanto also seems to have known that every number can be written as the sum of four squares. If he did indeed know this result, it would be truly remarkable, since even Fermat, who asserted the result, did not provide a proof, and the question was only resolved when Lagrange proved it using Euler's results. Although Diophanto did not use sophisticated algebraic notation, he introduced an algebraic symbolism that used abbreviations for the unknown and for the powers of the unknown. As Vogel writes, the symbolism that Diophanto first introduced, and no doubt devised himself, provided a short and easily understandable means of expressing an equation. Since an abbreviation is also used for the word is equal to, Diophanto took a fundamental step from verbal algebra to symbolic algebra. One thing will become clear from the examples we have cited. Diophantus was more concerned with particular problems than with general methods. The reason for this is that, although he made important advances in symbolism, he still lacked the notation necessary to express more general methods. For example, he had notation for only one unknown, and when problems involved more than one unknown, Diophantus had to express in words first unknown, second unknown, and so on. He also lacked a symbol for a general number, n. Where today we would write 12 plus 6 times n minus 3 times n squared, Diophantus had to write in words a number 6 times greater, increased by 12, divided by the difference by which the square of the number exceeds 3. Despite the improved notation that Diophanto introduced, algebra still had a long way to go before truly general problems could be written and solved concisely. Fragments of another of Diophanto's books, on polygonal numbers, a topic of great interest to Pythagoras and his followers, have survived. This work, according to the reference, states that it contains, quote, little that is original and is immediately distinguished from arithmetic by the use of geometrical proofs.
Diophantus himself references another work consisting of a collection of lemmas called the Porisms, but this book is completely lost. We do know, however, of 3 lemmas contained in the Porisms, as Diophantus references them in Arithmetica. One of these lemmas states that the difference of the cubes of 2 rational numbers is equal to the sum of the cubes of 2 other rational numbers. That is, given any numbers a and b, then there exist numbers c and d such that the cube of a minus the cube of b is equal to the cube of c plus the cube of d. Another extant work, entitled Preliminaries to the Geometric Elements, which has been attributed to Hero, has been recently studied, and it is suggested that the attribution to Hero is incorrect, and that the work is actually due to Diophantus. The author of the article believes he may have identified yet another work by Diophantus. He writes, "We conjecture the existence of a lost theoretical treatise by Diophantus entitled Teaching of the Elements of Arithmetic. Our assertions are based on a scholium by an anonymous Byzantine commentator." European mathematicians did not become acquainted with the treasures of Diophantus's Arithmetica until Regiomontanus wrote in 1463, "No one has yet translated from Greek into Latin the 13 books of Diophantus, in which is hidden the very flower of all arithmetic." Bombelli translated much of the work in 1570, but it was never published. Bombelli, however, borrowed many of Diophantus's problems for his own algebra. The most famous Latin translation of Diophantus's Arithmetica is by Bachet in 1620, and it was this edition that Fermat studied. Fermat was certainly inspired by this work, which has become famous in recent years due to its connection with Fermat's last theorem. We began this article by noting that Diophantus is often considered the father of algebra,
but there is no doubt that many of the methods for solving linear and quadratic equations date back to Babylonian mathematics. For this reason, Vogel writes, Diophantus was not, as he was often called, the father of algebra. However, his remarkable, though unsystematic, collection of indeterminate problems is a singular achievement that was not fully appreciated and developed until much later.
And so, at the end of this journey through time and theorems, realize Diophantus was not a man of statues but of equations. Many centuries later, his mysteries still echo with us. If you're intrigued by his mysteries, stay tuned. In the next video, we'll explore another wonderful story. Subscribe now, like it, and comment. So I'll keep you updated on the next mathematical journey. Together, we'll decipher Diophantus's enigma for the modern world.